In a typical IoT architecture, we see three different components: edge node, fog node, and the cloud node. The most familiar component is the cloud node, where we all know about the data centers and the cloud computing, where the data is being sent to a particular location far from where you live in. And then the data get processed and the results sent back to you. We have seen well-known brands like Microsoft, Google, Amazon have their own cloud platforms. But additionally, now to support specifically the Internet of Things systems, all of them have developed a custom cloud computing solutions that are specific to IoT. So in the Microsoft world, you can see Azure IoT. Then the Amazon Web Services has their own Amazon IoT, IBM Bluemix IoT, Watson IoT. There are so many different IoT platforms. Most of the big cloud computing vendors do have their own cloud computing platforms. And also there are open source and small companies who are also providing specialized IoT cloud platforms. So Car is one of those platforms. You will be using something called ThingsBoard later during the course. There are many IoT platforms come and go. The name get changed, so don't bog down the specific name. They rebrand, every vendor rebrand their own cloud platforms over time. But that is the component that every IoT application has, because at some point you need to do some kind of centralized processing with large amount of data. The two components that you may not be familiar with is the edge and the fog. If we introduce the edge computing more formally, edge computing is a distributed computing paradigm that brings computation and storage closer to the location where it is needed to improve response time and save bandwidth. So if you try to understand these ideas, the best way to think about is the data flow. So if you think about a smart watch, which is wearable in your hand, so that is the location where the sensing happens and then the data starts. And then from that, the data moves from your watch to your mobile phone, and then from the mobile phone to the cloud. So if you assume the more simplistic IoT system application architecture. So in that case, your wristwatch is the edge node, which is the least powerful. Mostly it is a microcontroller based. And then the data moves to the fog node, which is a bit more powerful, which is your mobile phone. And then data travels to the cloud node, which is we say that it is unlimited power, but of course there is some limitations even in the cloud, but for the discussion purposes, it is the infinite amount of resources. So typically the sensors are attached to the edge node, where you can gather the data from ECG or temperature or humidity or whatever that you need to gather. So in order to help this kind of edge computing, people have developed different microcontroller boards. So you will be programming one of those boards from Arduino, but there are many other solutions existed to help this edge domain, which is Intel had a version called Edison, and Microsoft also had a version called Gadgeteer, both no longer available. But if you look at the history of the evolution, you can see that this edge node is a category of devices people develop hardware and software for. They are microcontroller based, which means you will learn at a later stage that they don't have a particular operating system. They run in a kind of a loop, very, very simple. You have to do everything yourself, very small amount of memory, but it's very high speed. So because you know the predictability, because there's no other programs run on microcontroller other than the one that you write. So very straightforward in that sense, but you have to manually do everything like memory management and reading, writing data from sensors and everything. So programming is more like embedded programming, Increasingly, it is easier because of the previously we discussed about the development environments other people have developed. Because of that, it is easy to develop than before, but still it is not comfortable as Python or Java where you use in a normal traditional web development or a mobile development environment. And then the fog node, we also call it single board computers, which we briefly discussed before about Raspberry Pi. But there are other boards from different vendors as well. A Dragon board is one of them, a Beagle board. There's an Orange Pi as well. And then you can see near the Dragon board, there is an industrialized version of a fog node, which is more like a ruggedized version where you have developed the components, the computers within it in order to withstand vibration and high temperature or high humidity kind of scenarios. But internally, the more logical view is more like a single board computer, which you might run a operating system of your choice. There are many operating system vendors for this fog node as well, including Windows, but not the most popular. There are a lot of Linux variations. There's a Raspberry Pi OS. There are increasingly more choices of operating systems come into play in that fog node. So this is the overall architecture. So to summarize, you have the microcontrollers, single board computers, and the data centers, where you try to do most of your processing on the edge node. The reason is that data communication takes time and also take more bandwidth. And you will also learn that processing is cheaper in terms of energy consumption if you are battery powered than any kind of communication. Even like low energy technologies like Bluetooth consumes more energy than actually computation. So if you can do the computation, it is ideal to do the computation on the edge node and then pass on to the aggregated data into the fog node, and then it will also do some processing and send to the cloud. So that is the basic architecture of Internet of Things. And these are the three main components you will see in some form or fashion in all kind of IoT applications. It will be, of course, more complicated. There will be more number of edge nodes. There will be more number of fog nodes, but you will see more like a hierarchical architecture where the cloud is on the top and there are a lot of nodes on the edge, and then more nodes on the fog, but it is not as much as the edge nodes. So it's like a tree structure where data are going upwards to the cloud, and then decisions or the commands come down that on the tree. So we'll be discussing these in details over this lesson. This is the same architecture we discussed in the previous slide, but now I have replaced more electronic components with actual devices to give you an idea. So we already talked about the smartwatch, but in the edge node, you can see lights, door locks, refrigerators. So we broadly call them embedded devices. And these devices usually use short-range, low-power communication technologies like Zigbee, Z-Wave, Bluetooth, Wi-Fi, wireless HART to communicate with the gateways. So now we use the term gateway in a more natural language, but more technical term would be like a fog node. And these fog nodes or the gateways do the job of connecting multiple edge nodes together. So they will collect all the data, do some kind of processing, and then send it to the cloud node using 3G, 4G, Ethernet, TCP/IP. So this is the more natural view that what you see in the real world. But behind the scene, we previously saw the electronic level, how this works. I briefly talk about the tree structure in the IoT architecture. So as you can see in this diagram, there are multiple edge devices where the sensors and actuators are connected. Sensors are collecting data and then sending to the gateway. So the data get pre-processed in the gateway and then sent to the cloud IoT platform, and then cloud platform will forward the data into different application services and then do the management of data. And then the cloud platform will send back the commands to the gateway as well as to the devices. As you can see, each gateway is connected with multiple devices, and then there are multiple gateways are connected to the cloud platform. So this is the typical architecture, the tree structure we discussed earlier, and also the characteristics of this architecture that you need to keep remember is the computer power, memory, storage, and bandwidth. So these are the 4 considerations or the characteristics that you need to think about when you are designing your IoT application system. So you need to make sure that depending on the task at hand, you have necessary amount of compute, memory, storage, and bandwidth capabilities on different part of the IoT application. Because this is a very simplistic diagram, the actual IoT systems could be quite large, heterogeneous. There are many data communications happen. So each of these data communications you need to separately analyze and understand what kind of requirement each of these devices and gateways need to be. So far, I explained how the IoT architecture works and what are the main components, and I briefly talk about the hardware components of each of these components. Now I would like you to go to the software part of this, the IoT software stack. So IoT software stack is not something standardized. So increasingly people develop different IoT software stacks. So what you going to see in this slides and in subsequent slides are some kind of conceptual framework that people have developed over time. But because the IoT is fairly new, there is not maturity. So you might not see all these different software components or the features in all the IoT software frameworks available at the moment. So these are the generic conceptualized version of the IoT software stack most people have developed. So in this IoT software stack, they use the term called constraint devices to say it is an edge device or edge node, or in other terms, microcontroller devices. So as you can see, the software stack is smaller because the resources amount of resources they have are quite small. So it has to be the lowest amount of resource requirements for that particular node. On the gateways, we also see a little bit more sophisticated software stack, which has operating system. So if you note that in the constraint devices, you don't see an traditional operating systems. They are more either no operating systems, or it could be like real-time operating systems, which is a very stripped down version of a traditional operating system. And then you can see application runtimes in gateways, different protocols it's supporting. It also support network management, connectivity, data management and messaging, because now the gateways are in between the cloud and the constraint devices or the microcontrollers or the edge nodes. So the multiple edge nodes are communicating with the gateway. So you need to manage those different communications. So it has to have some kind of management framework there. And then the cloud platform, you probably all of us know, talk about the connectivity. So you need to manage the connectivity with multiple gateways. You have to have messages routing, different data management, storage, device registries, user registrations, event management, complex event processing. So you need to detect certain events in real time. Event detection are something sometimes people have frameworks within the gateways as well, but the majority of the event detection could also happen in the IoT cloud. And then across these range, security is a big part, and then also the ontologies, and then the toolkits and the SDKs are supported across these devices. So still the support is not as much as for a mobile or a web development, but it is increasingly getting better. We have come a long way from having these kind of programming allocated to specialized embedded developers to be able for a normal computer science or software engineers to be able to develop these software IoT systems. So over time, there are a lot of tools and SDKs, but it is not as mature as mobile or a web application development at the moment. Over the next few slides, we can go a little bit more detail into each of these concepts we discuss here. First, let me introduce the functionalities of the Edge node, which is the most simplest node and the most resource-constrained node. So there are three key functionalities they usually provide. But as I said before, this doesn't mean that this is a universal functionality list. Each individual vendor or the software developer might develop their own set of functionalities that they think useful for the Edge node. But these are the commonly typically see functionalities in an Edge node, which is a microcontroller. So first, you will see an hardware abstraction, which means that you will be able to access GPIO pins, serial input-output, memories. You'll be able to call different methods and read the data from sensors, store the data, communicate with serial interfaces. Those kind of basic functionalities will be available through a programming API or a language. So you will be using more like a C++ inspired language to communicate with the actual hardware. So there is a framework in between the hardware and then your program. So you can easily write the programs in a high level. But it may not be high level as much as like Python or a Java. So you might need to do a lot of work from yourself, like reading strings and things like that. You might need to use your own loop rather than calling functions. Increasingly, some people provide those functionalities, but because of the resource constrained nature, the more functionalities they provide, the more consume the more memory of that or the storage of that particular device. So it is quite often you see that bare minimum support, and then you have to either write your own code to do certain tasks or use some other frameworks to do that for you. But by default, it comes with a bare minimum because of the resource constrained nature. Then the communication support. There will be often driver support for a wide range of protocols like Bluetooth, Zigbee, Thread, CAN bus, MQTT, all these different both communication and application level, network level and application level protocols. So it's easy for you to write few lines of code and establish a connection between two Bluetooth devices. And also you will see remote management. So you will be able to remotely upgrade the firmware of the resource constrained devices or the Edge node, and then do some tasks like monitoring the battery level, whether they are sleeping or alive, keep track of when they sent the data last time. So those kind of functionalities will be available to you. So these are the basic minimum functionalities most of the systems, IoT software stacks provide. Now we are going to talk about the functionalities of a typical fog node. So you will see operating system in a fog node. So it will be a general purpose operating system like Linux. There's a Windows version, there is a Raspberry Pi version. There are many different operating systems. Even Google had their own version, probably now discontinued. But there will be more and more operating systems joining in this particular market segment where they are stripped down version from a traditional desktop version, but also they provide more capabilities and easy to deal with rather than microcontrollers. They also will have application containers or runtime environments. So you will see that you can write an application code in your application remotely and then push it to the gateway remotely and dynamically update. So that you will see application containers. You can create the entire container or some kind of runtime. You can see this in machine learning or AI, where you can write everything in the TensorFlow and then maybe push it as an application or a service or a container to the gateway node, where they will perform some kind of a AI analytic on temperature data or even camera data. Similar to the Edge node, you will see the communication and connectivity. Now you need to manage connectivity between both sides, which is the edge node connectivity between the fog and the edge, as well as the fog and the cloud. Because of this more complex communication, you will also see data management and messaging. They will allow local persistence of network latency, offline modes, real-time analytics, and other data management tasks of storage, aggregating, storing the data temporarily until it is been sent, those kind of things. And then you will also see remote management, similar to the edge devices. They will be able to remotely configure firmware update for the fog node, starting and shutting down, deploying new applications, and then pretty much manage the gateway devices remotely. So there'll be a framework to do that. So these are the common functionalities of a fog node. Theoretically, the functionalities offered by the cloud node is pretty much unlimited. But what are the common functionalities provided by IoT platforms are these. First, you will see the connectivity and message routing. So IoT platforms need to manage communication between large number of gateways using different protocols, different formats. So you need to be able to get these data, understand, and then format into a common data structure so the data analytics can happen. Device management and device registry, you need to keep track of what are the gateways and what are the devices connected to those individual gateways, because when you want to send a command, you need to know where the device is. So how to reach a particular device. So you need to keep these devices in a kind of a registry, so you know how to reach them. Data management and storage. So a lot of data that comes from sensors, from the edge nodes. You might want to store them for a longer period. So you will need to handle the data management and storage, event management, analytics, and user interfaces. So most of the end users or the people who manage the IoT platforms directly interacting with the cloud platform. They never interact with the gateway or the device directly. So the user interface is on the cloud, and then they use it as a proxy to reach to the different devices and even update firmware or deploy analytics. Large scale analytics usually happen on the cloud IoT platform. The reason is that sometimes on the edge device see only the data that it has, which means the sensors that is connected to. But the cloud has the bigger picture. So they have the data from multiple different devices, from multiple different gateways. So they can compute certain high-level analytics on that. And then event management. Certain event management are now we see happens on the edge and the fog as well, like triggering if the particular temperature is going above a certain level or something like that. Very small level of event, but more complicated event management tasks will happen, or detecting particular complex patterns will be detected in the cloud when the data reach to the cloud. So then the analytics, as I said, will happen in the cloud as well. Then the applications actually get access to the data from the IoT platform. So usually the IoT platform is some kind of an intermediary or a middleware that allows the IoT software developers to develop their own IoT application. So IoT platforms are quite generic. They provide certain number of functionalities, and then the IoT developers would get the data from the platform using an API, and then do whatever they want with the data. It's up to that. After that, it would more like the web or a mobile domain where you get the data and then do the processing in whatever the way they want. So the platform's job is to make easier to for developers to get access to the data, and then don't worry for being managing these devices efficiently. So the cloud platform, IoT platform, will take care of these mundane tasks on behalf of the developer. So these are the common functionalities you see in the cloud node. So far, we discussed about the IoT software stack across different components. Now let me introduce the key characteristics of for IoT stacks. So IoT stacks are usually loosely coupled. So these stacks can be used independently from each other. So probably you can use one stack from one vendor on the edge node and then use the fog stack from another vendor. So we increasingly see this kind of cross communication between different vendors across the different components. It is also modular, so we can see both on the software and hardware side, increasingly these for each node, for example, different software and hardware modules available for each node. You can increase the number of sensors or actuators, and then you can easily write programs to use those sensors using the modular frameworks. You can import certain packages and start programming them. And then you can see on the gateways, you can deploy application containers. You can ship them remotely and then develop different modular architectures like microservices and then deploy them on the fog node. Platform independent is slightly complicated. On the cloud end, you have the ability to run IoT cloud platforms on different service providers. So you can have get a ThingsBoard open source IoT platform and then deploy them in Azure Cloud or IBM Watson Cloud. But when the big vendors like Microsoft and IBM, when they have their own IoT platforms, they only work on their only platform as a service offerings. So you can't get Azure IoT platform and deploy on your own servers. At least at the moment, it is not supported. So you are somewhat attached to certain vendors. But what we see is from the fog node, you can deploy different stacks on the fog nodes like Raspberry Pi. So you can get a Pi and then deploy any stack. So the Microsoft has their own stack, Eclipse have their own software stack on that, or you can write their own application stacks to the Raspberry Pi. So when we come to the microcontrollers or the edge nodes, the interoperability becomes slightly complicated because edge devices are designed to be more optimized to a particular task. So if you add certain generic purpose functionalities to the edge node, it will increase the requirement of the computation and memory to manage that particular framework. So that is why most of the time you will be developing your own programs on the edge node. Most of the IoT platforms, both hardware and software, as we discussed very earlier as an enabler, they are open source and they are interoperable. That is one of the key reasons that IoT become so popular and being adapted so fast. IoT stack also have defined APIs. What does this mean is that when you're developing a software stack for fog node, for example, a ThinkBoard has functionalities that you can integrate with other open source softwares like stream processing software like Kafka. So they have defined APIs. They can easily integrate other applications. So IoT is most likely, even more than the web and mobile application development, there are a lot of pre-built components putting together kind of scenario. So if you become IoT developer, you will see that most of the time, rather than developing applications yourself, you will be combining different hardware and software, different APIs and frameworks together to achieve or design your design and develop your IoT application. It will be very limited times that you will be required to go and develop your own code. So you will be basically connecting some open source and more commercial software together to achieve your task. Because if you try to develop everything by yourself, from cost wise, it doesn't make any sense, because the cost will rise very fast if you try to develop your own APIs and frameworks for yourself. So you'll be using quite a lot of other people work in IoT more than that you use in a mobile and a web domain. Now I would like to bring your attention to IoT gateways. So previously we discussed that IoT gateways are more like the fog node. They are pretty much the same, but IoT gateway is a terminology most of the people in the industry use. So it is good to know and understand IoT gateways a little bit better. You can think of IoT gateways as a more special case of fog node. It is a fog node, but people identify it with a particular terminology, and then there's some informal attachment of certain functionalities to the IoT gateway when people refer to that. So IoT gateway is a physical device or a software program that serves as the connection point between the cloud and the microcontrollers, sensors, and intelligent devices. So we already talk about this as you know, that fog devices are in between the edge and the cloud. So the data moves across the gateways from both sides. They integrate protocols for networking and different application level protocols as well. They should be able to perform certain amount of storage of data, and then perform certain amount of edge analytics. They're also responsible for secure communication and the management of security, because especially from the edge nodes, they have very limited capabilities in terms of security. But edge gateway is the device where they do security key exchange between the edge devices and the fog node, so make sure that the data is encrypted and secure. There's a small video on what is IoT gateway. Please go and watch it and come back. Here I have put together a slide where I combine different open source IoT solutions, especially developed and managed by Eclipse organization. So it is an open source software that develop different frameworks for IoT. So you can see there are purpose-built software for data aggregation, security, device management, event management, and digital twin. Some software stacks or frameworks are more mature than the other, and then by the time you watch this video, they may get more matured or they may be discontinued. But the idea is that there are a lot of open source community who develop software to help IoT developers. As I discussed before, most of the time your responsibility is to find the best framework for your task or for your IoT application and use it as much as you can, rather than developing anything by yourself. So that is the power of having a community where you can quickly put together an IoT application by adopting different frameworks and combine them together. So the key skill that you need to develop is to be able to understand what each of these framework does and be able to pick the right software framework for the right job.